lecture we are going to start a new topic, basically thermodynamics of phase equilibria. That itself is a topic. So, we will start summarize what we have gone through last few lectures. We have discussed that for an open system the differential form of u can be written as TdS minus PdV plus summation of mu I dni. So, this is for an equilibrium system. Okay, and we also know from the Euler's theorem that u is equal to Ts minus PV plus summation mu I d mu I this should be Ni. Okay. So, what we have done is basically we integrated this and using the extensive property we got this expression. Similar to u, you can show that H is also Ts plus summation mu I Ni, A is also minus PV plus summation mu I Ni, and G is summation mu I Ni. So, that is what we know that. Okay. Now, making use of this and as well as the differential equation, what you can do, or differential expression of the potentials, what we can do is we can come up with an expression called Gibbs-Duhem equation. Okay. Equation or relation. So, what it does, it gives you a constraint between intensive variables. Okay. So, it tells you that considering that this is a constraint and you can obtain from either of this, either of the potential function. Okay. So, it tells you that n plus 2 for any change in state you need n plus 2 variable, intensive variable, but only n plus 1 can vary, okay, independently. Okay. Now, what we are going to do is we are going to apply this to the equilibrium conditions. Let us just consider that you have a phase, many phases can be considered at equilibrium. Okay. So, you can have phase 1, phase 2, phase 3 and so forth, and phase pi. Okay. So, there could be these many, because there is no condition of that maximum number is limited to 2 or 3 as far as the equilibrium phases are concerned. You can consider, let us say, arbitrary pi phases which are at equilibrium. But considering the thermal, mechanical and chemical equilibrium, that for each phases, if I consider, let us say, Ti is the temperature of the phase I, Pi for pressure of the phase I, and mu I, then at equilibrium what are the conditions? There is no net heat flow, okay, there is no net movement of the boundary, and there is no net mass exchange. So, no net heat flow would tend to give us this condition that T1 is equal to T2, and this is same as T of pi. No net boundary movement would give us P1 P pi. No net mass transfer would give us mu1, or instead of this we need to also define, because if they are let us say n component, right, then we have to define mu I in phase 1, that should be same as mu 2 in phase 2, mu I in phase 2, and that should be same as mu I in phase pi. Okay. So, this is the condition we have. Now, if you want to find out the number of variables which you can independently vary, okay, that is what we call a degree of freedom, then we can make use of these equations. So, how many conditions of the constraints we have been put here for an equilibrium? If they have pi phases, then they are pi minus 1 equation, okay, T1 independent equation, T1 equal to, or constraints, T1 is equal to T2, okay, T2 is equal to T3 and so forth, right. And there are n plus 2 here number of variables. Okay. So, what I can write is for each phase you have n plus 1 independent variable. Okay. So, that means the total number of variables is, why the n plus 1? Because you have the one which is constrained by the Gibbs-Duhem equation. So, for each phase you have n plus 1 variable. So, total number of variables are pi multiplied by n plus 1. Okay. These are total number of variables, and how many constraints we have? Constraints, that will be, so if you look at it, these equations are pi minus 1, okay, and this number of variables are, because so this is 2, temperature and pressure is 2, and this I is n, okay, that means n plus 2 multiplied by this is pi minus 1. For each variable we have pi minus 1 constraint. So, that means total constraints are this. So, degree of freedom is total number of variables minus the number of constraint. So, this gives you n plus 2 minus pi, and n is number of components. One can also write, let us say, c plus 2 minus pi or c plus 2 minus p. These are same thing, right, because c is number of component. Okay. So, this is what you call it Gibbs phase rule, right. Since we have defined this particular expression, okay, this is something which was defined using Euler theorem for thermodynamic function, which was basically all these are extensive function. We can generalize this by considering arbitrary E as a function which is extensive function. So, I am trying to now relate this and define something called E, okay, which stands for any extensive property. Okay. So, what I am trying to do is basically connect the chemical potential to partial derivatives of these extensive properties. Okay. And from there we would like to get some idea how to get this chemical potential, and then we will realize that this is more ambiguous, so it is difficult to do that, and then we will try to introduce something called fugacity. Okay. So, let us consider E, which stands for any extensive property. E could be anything, E could be energy, U, H, V, etc. Okay. Could be U, H, V, etc. Okay. Now, I am going to define a partial molar value of E. Okay. Let us say for ith substance or ith component in the mixture. Okay. So, this is the definition, is basically partial derivative of E with respect to n I, okay, keeping temperature, pressure and all other components, amount of components fixed, that means n I is not equal to n j. Okay. So, example could be U I, which is del U by del n I T P, and for all possible j's, such as j is not equal to a. Similarly, you can also come up with V I. Okay. So, this is something which you are already aware of it, right. So, what I am trying to do with this definition, okay, is to write expression E, which is a function of T P n1 till n, and come up with a differential form, a generic differential form. Okay. And we will show that you can also obtain a generic expression what we have got into differential form for other known thermodynamic functions for any extensive property. Now, remember that for total of the molar value our molar property is typically let us say for small e we define as a molar property, which is like E divided by total number of moles, or E divided by NT. Okay. So, we are going to use small variables to define molar properties. Okay. Whereas the partial molar properties are the big symbols with a bar on top of it. Okay. So, let me just write this E, which is basically a function of Tp. So, let us assume that this is a function of Tp and all this moles of different component. So, dE is, of course, we are going to take it as partial derivatives. Okay. So, this means basically all of this, right, dt plus del E by del P T N I plus summation del E by T P and N J such that N J such that J is not equal to I. Okay. Now, if you compare this expression to the expression of, let us say, Gibbs free energy in the differential form. Okay. So, let us compare this to dG value minus S dt plus V dP plus summation mu I d I. Okay. So, it is more or less basically if you replace E by G, you get exactly the same expression with the partial derivatives of del E by del I, and I is nothing but mu I. Okay. So, now given this, okay, you can integrate this and we can obtain a generic expression using the Iodo theorem as nothing but E partial molar property of E with respect and multiplied by Ni. Okay. So, this is a very straightforward exercise. This you can do that exactly the same as you have done for getting G is equal to summation mu I N I, because here this is nothing but E I bar. Okay. So, when you integrate this, you get exactly this as the same way as you have done for other cases. Okay. So, this particular exercise can be done for any extensive variable. Okay. But here in this case, the reason why you are getting this, because of the fact that what is the component of the extensive variable, because here E is Tp n1 to n. So, here the homogeneous function of only n variables. So, you can do this exercise. This is something which you must have done in your earlier courses also. Okay. As I said, this is true for any extensive property. So, if you replace E by U, this would be your U is equal to summation ui bar Ni. If you replace E by H, this is going to be similarly E will be replaced by partial molar enthalpy. Okay. So, in other words, I can actually use this information to get U as summation ui Ni, V as summation Vi Ni, A is summation Ai Ni. So, we can write now any extensive property as a summation of partial molar property multiplied by the number of moles of that particular component, where I summation is over the number of components. Okay. Now, since G is summation mu I Ni, which means basically if you compare these two expression means mu I is G I bar. Okay. So, chemical potential is nothing but partial molar Gibbs free energy or species I. Okay. So, let me just describe one more thing. So, there is a relation between these molar quantities You know H is equal to U plus PV. If you want to write that in the partial molar quantities in the form of that, you can simply write HI bar is UI bar plus PV bar. Similarly, you can write mu I, which is basically GI bar, is nothing but HI bar minus T SI bar, okay, because G is equal to nothing but H minus T. Yes, so you can write in the same form. I can try to exploit this, and this is something which I am going to get this expression of partial derivative of mu in terms of the variables which are experimentally accessible. Okay, so let me just come up with the two important relation. Okay, so let me start with dg is equal to minus s dt plus vdp plus summation mu I dni. Okay, I can make use of Maxwell's relation, okay, and come up with this expression that del mu I by del p at constant t, ni and all other j, this should be equal to del v by del ni, temperature, pressure and keeping nj constant. Okay. So, this is, if you look at this expression, you can directly get this expression from this Maxwell relations. Okay. What you are doing is you are taking the derivative of this with respect to p, keeping temperature constant and all other constant. This should be same as what if you are keeping nj constants, what remains is basically mu I dni. Okay, and that thus you should be getting del mu by del p, that should be equal to del v by del I ni. So, remember this conjugate variable, we may try to make use of it. Now, given this expression, this is nothing but vi bar. Okay. Similarly, using the same fundamental equation, we can also write okay. So, again using the Maxwell relation here, we are getting this, that minus of partial molar entropy of component I is nothing but the partial derivative of the chemical potential with respect to the temperature. Okay. And partial molar volume of component I is nothing but partial the differentiation of chemical potential with respect to pressure. Okay. Now, for a pure system, of course, you can write this as for pure del mu by del p at T, this is molar volume, and del mu by del T at P is minus molar entropy, and we are going to use these two expressions in the later case. Now, let me end this part of this discussion by considering the fact that I can also connect the partial derivative of mu to something which is more measurable. Okay. So, not just entropy, and how am I going to do that? By considering that mu I is nothing but G I bar is equal to H I bar minus T S I bar. Okay. And now S I bar is this expression, this. So, I can write this as H I bar minus T del mu I by del T at P and N constant. Okay. So, if you rearrange this expression, I should be able to derive this in this form, minus H I bar by T square. Okay. For a pure system, this is equivalent to saying that this is nothing but minus molar property for a pure system, right. Now, in this case what we have done is we have connected the changes in the chemical potential with respect to temperature to something which you can measure, enthalpy. Truly speaking, there is only enthalpy change, okay, which we can measure. Now, this brings to a question about chemical potential. Okay. So, I will stop here, and in the next part we will continue with the chemical potential and its relation with the fugacity.